Welcome back to the Deep Dive. Today we're getting into a material science discovery that is, well, it's already being called the foundation of the 21st century chemical industry. We're diving into the 2025 Nobel Prize in Chemistry, awarded to Susumu Kitagawa, Richard Robson, and Omar Yaghi for developing metal organic frameworks, or MOFs for short. And our sources on this, everything from academic papers to industrial patents, they all frame this as a huge leap forward.
It really is. This prize validates decades of work. It establishes MOFs not as some niche material, but as a completely new way to think about designing solid matter.
So our mission today is pretty straightforward. We need to figure out what this Nobel-winning material actually is, how its unique structure gives it these almost supernatural abilities, and most importantly, what this means for you, for all of us, when it comes to huge challenges like energy and climate change.
Okay, let's unpack this. And I think we have to start with the architecture. The structure is what makes MOFs so revolutionary. You have to forget about traditional materials, those rigid, solid blocks. MOFs are something else entirely. They're like a molecular scaffold that's, well, it's essentially more empty space than solid material.
Exactly. The real breakthrough is in how they're assembled. Picture it like molecular construction, almost like a skyscraper that builds itself.
Okay.
MOFs are these crystalline frameworks, and they're built from just two crucial components that repeat over and over again.
Right, so the first component would be the anchors of the structure, the metal ions or clusters.
Yes, those act as the nodes or the pillars. They're the strong, rigid connection points, the corners of the structure, you could say. The concrete foundations holding it all together.
And the second part is where the organic piece comes in. You have the carbon-based organic linkers.
These are the beams.
The beams, the struts, exactly. They connect the metal nodes, and they're usually these rigid, wad-like molecules that, they determine the size and the shape of the empty spaces in between.
Whatever sources had a great way to visualize this. Imagine a huge, perfectly organized hotel with thousands of empty rooms all stacked in a perfect grid. That's a MOF.
That's a perfect analogy. And the key insight is that the empty space, the rooms in that hotel, that's the working part of the material.
I see.
The whole thing is based on what we call coordination chemistry. It's a self-assembly process where the metal ions and the linkers are attributable to each other and they form these strong bonds, but they do it in a way that leaves behind these huge open voids.
But if it's mostly empty space, doesn't that make it fragile? Are these things actually strong enough for, real-world industrial use?
That's a fair question, and it was a huge hurdle in the early days. A lot of the first MOFs would just collapse.
Right.
But the Nobel-winning work showed that by carefully choosing your nodes and your linkers, maybe choosing a stronger, more rigid organic piece, you can engineer a framework that is both incredibly porous and stable. And you need that stability so those empty spaces can do their job.
Which is capturing things.
Capturing, separating, preserving, all sorts of things.
Okay, so we get the structure. Now here's where it gets really interesting. Moving from the what to the how. Because it's one thing to make a porous material, but MOFs have a capacity that is just astonishing. Our sources all point to one key property: their extremely high internal surface area.
This is the number that really shocked the scientific community. The amount of internal real estate is staggering. To give you some context, a classic high surface area material like activated carbon, which you'll find in, water filters, gas masks.
Everywhere.
That might give you up to 1,000 square meters per gram, which is already a lot.
But MOFs just blow past that.
They completely shatter that record. Some MOFs have been made with an internal surface area of around 10,000 square meters per gram.
Per gram,
It's hard to visualize. You're basically fitting the surface area of a large athletic field into a single teaspoon of this powder.
10 times the capacity of what we thought was state-of-the-art. So why is that huge capacity so important? What does it let you do?
It means the MOF acts like the ultimate molecular sponge. It uses all that internal space to attract and hold on to thousands and thousands of molecules. It works through adsorption. That's molecules sticking to the surface.
And they can let them go too, right?
Critically, yes. That's desorption, the controlled release of whatever you've stored.
And this brings us to the second big insight, the one that really sets MOFs apart from older materials like zeolites. And that's tunability, or designability.
This is the real game changer. It's the difference between finding a tool in nature versus engineering the perfect tool for a specific job. Zeolites, for example, are fantastic. They're stable, reliable, but their pore sizes, their chemical properties, they're fixed by nature. You get what you get.
But MOFs are synthetic.
Entirely. Because you can choose the metal node zinc, copper, whatever you need, and then choose from literally thousands of different organic linkers. You can customize the MOF's properties with just incredible precision.
So if I wanted a material that only traps, say, carbon dioxide molecules but lets everything else pass through, I can basically design the perfect molecular cage for CRO.
Precisely. You control the pore size down to the atomic level, and you control the chemical environment inside that pore. You can make the interior surface chemically sticky only to QO. That's what we call highly selective adsorption. And that level of control is what makes this so revolutionary.
Which is why this isn't just an academic prize. This translates directly into solving some really big global challenges. So let's get into the applications that earned this Nobel, starting with environmental protection. The most obvious one is QO capture.
Right. MOFs give us a way to remove carbon dioxide, either directly from the air or, more practically, from industrial smokestacks before it ever gets into the atmosphere.
And the challenge there has always been the energy cost, right? It takes a lot of energy to grab the CORO and then release it again so you can reuse the material.
Exactly. But with MOFs, you can design them to trap CRO with a very small energy input and then release it with just a slight change in temperature. That makes the whole cycle much more economically viable than the older energy-guzzling methods.
And sticking with the environment, there's water production. This one sounds like science fiction, but it's happening. Pulling clean drinking water out of dry desert air. Our sources describe MOFs that are engineered to just soak up moisture from the air at night. Then, during the day, the heat from the sun makes the MOF release that moisture as pure, clean water.
It's a completely passive system. No big energy grid, no complex pumps. You're just using a material that cycles with the sun. It's an incredible idea for arid regions.
So beyond the environment, what about energy storage? We're moving towards things like hydrogen power, but storing hydrogen safely is a huge bottleneck.
A huge bottleneck, and MOFs help solve the density problem. Instead of having to use incredibly high pressures or cryogenic temperatures to store hydrogen,
Which is dangerous and expensive.
very. Instead, you can store it inside a MOF. The gas molecules basically just stick to that massive internal surface area, letting you pack way more fuel into a smaller, safer container at much closer to normal conditions.
And what about in medicine? I saw some fascinating applications there.
Oh, absolutely. In chemistry, they're amazing for things like gas separation, but in medicine, the big one is drug delivery.
How does that work?
Think of the MOF as a tiny, protective, and very stable cage. You can load it with a drug, maybe a powerful anti-cancer agent. The MOF structure protects the drug as it travels through the body.
And then it just releases it all at once.
No, and that's the genius of it. It offers sustained release. The framework slowly degrades, or the drug diffuses out, providing a steady, controlled dose over a long time. This means less toxicity for the patient and more effective treatment.
It's incredible. To really get the historical scope of this, though, we should probably look at the one that started it all, right? The blueprint. MOF5.
We have to. MOF5, or IRMOF1, is the material that really launched the entire field. It was the proof of concept.
And what was it made of? What made it so special?
So it used a specific Zen-Euro metal cluster, that's a zinc-based node, and a very simple rigid organic linker called BDC.
BDC.
154 benzene dicarboxylate. Because that BDC linker is basically a perfectly straight rod, when it reacts with the zinc clusters, it forces them to assemble into this perfect 3D cubic structure.
And that cube shape was the key.
It was revolutionary because it created these huge, wide open, empty spaces. And it was the first time anyone had shown that this kind of material could store a massive amount of hydrogen gas. It proved, really, that you could make a porous material in a lab that was better than anything found in nature.
That kind of perfection sounds complicated to make.
Yeah.
How do you get thousands of these pieces to all line up so perfectly? You can't just stir them in a beaker, can you?
Yeah, no, you can't. The standard procedure is something called the solvothermal method. It's all about control. You dissolve your ingredients, the zinc salt and the BDC linker in a specific solvent.
Okay.
Then you seal that mixture in a vessel and you heat it under controlled temperature and pressure, sometimes for days. This slow, steady process allows the bonds to form very regularly, letting the components fall into their most stable energy state, which is that perfect crystal.
So we have this amazing tunable material. But what about the competition? We already have things like zeolites. And I've heard the COFs too. Why go all in on MOFs?
That's the critical question, because they're not perfect for every single job. Let's compare them.
Okay, let's start with the classic. Zeolites. The workhorses of the chemical industry. They're super tough. They can handle insane heat.
Right, and that strength comes from their makeup. They're purely Inorganics, just silicon, aluminum, oxygen, they're basically rocks. But that rigidity is also their biggest weakness. Their pores are a fixed size. You can't tune them.
So they're strong, but not adaptable.
Exactly. Then you have COFs, covalent organic frameworks. These are kind of the lightweight cousins. They're made of only organic components held together by strong covalent bonds.
No metal.
No metal, which makes them very lightweight and great for certain applications like electronics or some types of gas storage. But they lack that metal center, which is often what gives MOFs their unique chemical stickiness and control.
So MOFs, with their combination of metal ions and organic linkers, they're kind of the best of both worlds. They're not aiming for brute strength, but for optimization.
Precisely. MOFs are the Goldilocks material. They have enough stability for most jobs, they have by far the highest porosity, and, most importantly, you have total design control over the chemistry. The Nobel was awarded because they opened up a whole new universe of chemical possibilities.
So what does this all mean? We've gone from the architecture, these self-assembling molecular hotels, through their insane surface area, that 10,000 square meters per gram, and into these world-changing applications, sucking carbon from the air, pulling water from the desert. It's clear the work by Kitagawa, Robson, and Yaghi has set a new course.
It has. I think the real takeaway from the 2025 Nobel is that we finally mastered the ability to design empty space at the molecular level. We can control the size, the shape, the chemistry of these internal pores, atom by atom. We're truly in an era where materials are not just discovered, they are custom built for a purpose. And here's something to think about. If we can precisely engineer materials to filter, separate, or transport any molecule we choose, what happens when that technology becomes cheap and scalable? We really encourage you to look into concepts like selective absorption and nanoscale engineering. What boundaries fall next when we can design matter molecule by molecule?
Thank you for joining us for this deep dive into the world of metal organic frameworks.